Hi, my name is Pierre Vales. I'll be explaining how the stop and wait protocol works, how the simulation in Jupyter Notebook is structured, and how I modified the physical layer to behave like real, unreliable network. I'll also show some example outputs to demonstrate what happens during message transmissions. The notebook simulates two communicating hosts, Alice and Bob. Each host has three layers: the application layer, the data link layer, and the physical layer. The application layer, which you can see over here, creates and receives the user's messages. As you can see, it handles inputs. The data link layer, which is down here, adds frame numbers and manages acknowledgements to ensure reliable delivery. And the physical layer, which is over here, handles the actual transmission over the network using sockets. Each layer runs as a separate thread, which allows the system to send and receive data at the same time. To start, I ran all the cells in Jupyter Notebook to activate all the threads. Then I typed Alice to Bob in the Alice text box. Let's do that. Go to the text box. Here we go. Let's type Alice to Bob and submit. Here we can see some messages are being sent through. There we go. See? Um, in the output I saw, let's go to the examples I have. Uh, we have some messages. Here we have message Alice to Bob from Alice. Then Bob receives it. It calls the state, and then it sends an acknowledgement back. This shows that Alice's message went through all layers and reached Bob successfully. And then Bob immediately sends an acknowledgement. If a data frame is lost, as we can see over here where it says packet lost, Alice never gets an acknowledgement and retransmits, and you'll see Alice sending a resending frame number and then the message. And when an acknowledgement is lost, Bob detects a duplicate message, as we can see over here, and resends the acknowledgement without delivering the same data twice. So here we have received frame 3 but expected 4. Uh, uh, Bob just sends the acknowledgement again without sending the same data. These examples show how the stop and wait protocol maintains reliability even when errors happen. But next, I modified the physical layer to make it behave like a real network where delays and losses are common. In the loop tx function, where let me just find it real quick. Loop tx function, I added a random delay between 0 and 3 seconds. No, wait, that's the loop rx function. My bad, let me explain that real quick. In the loop rx function, I added a random delay between 0 and 3 seconds before processing received messages. And in the loop tx function, I added a 15% chance for a transmission to be lost and a 5% chance for it to be duplicated, as you can see over here. This confirmed, after running it, let's run all cells again. And when we type Alice to, oh, when we type Alice to Bob, and just start, see, we have a transmission duplicated over here. We have all messages have delays between 0 and 3. Let's see if we find a transmission lost. Here we have a transmission lost example. This confirmed that the modify functions were working. Messages were sometimes lost, sometimes were delayed, or sometimes were duplicated, just like in unreliable real-world link. Even with these problems, the stop and wait protocol still delivered the messages correctly. Lost frames were retransmitted, duplicates were ignored, and the acknowledgements were resent when needed. This experiment shows how each layer contributes to reliable communication. The application layer creates data, the data link ensures it's delivered correctly, and the physical layer handles real-world imperfections like loss, delay, and duplication. By modifying and observing these behaviors, we can better understand how communication protocols maintain reliability over unreliable networks. Thank you so much, and that is all.
Well, hello. My name is Diego PEREZ-GANDARILLAS, and I will be going over section 4 of the project 2 for the networks course. In this video, we'll be going over the implementation of the measurement layer entity, or MLE for short, which is responsible for collecting the transmission performance data in our stop and wait protocol experiments. The goal of this layer is basically to measure average delay, loss rate, message loss rate, and duplication rate between two nodes while interacting with the lower layers that emulate physical behaviors such as the aforementioned characteristics. Let's start with the constructor here. When the MLE object is created, it sets up the measurement environment and then the user interface for experiment. Inside the constructor, we create a button widget from IP widgets labeled start experiment. What this pretty much allows us is to manually start the measurement process like within the notebook. The constructor also defines a callback function that gets triggered when the button is clicked, and then when you press the button, the callback sends 100 messages to the lower layer by calling it the send function. Uh, each of these messages include like three important fields, which is the experiment ID, message ID, and the current like timestamp that we're like getting using that time in S, which gives us nanosecond precision. Uh, this information allows us to receive the node to later compute accurate one-way delays. And finally, the constructor initializes a few variables such as counters for total delay, receive messages, duplicate, and IDs, which will then be like used to calculate performance metrics once the experiment completes. Uh, moving forward quite a bit to a loop-rx function. Uh, this function runs continuously in the background thread and waits for messages coming from the lower layer. When a message is received, it starts to extract the experiment ID, message ID, and then send the timestamp. Then the function captures the current time using the aforementioned time ns, and computes the delay by subtracting the set time from the received time. Uh, to avoid counting any duplicates multiple times, it keeps track of every message ID that's already been processed using a set called received IDs. Uh, if a message with the same ID arrives again, it increments the duplicate counter instead of treating it as new. And then, like valid first time messages have their delay added to the running total, and their count is recorded to later compute the average delay. Throughout the process, the function also logs messages to the notebook, so we can see messages were received, their delay, milliseconds, and any duplicates detected. In summary, this is where the actual measurement and data collection happens. It's like the receiver side of the experiment. And then finally, for this like part of the notebook, there's the show results function, which after all the messages have been sent and received, we can call this function to summarize the performance metrics. This helps us view what like what was the performance, right? For the average one-way delay, the message loss rate, the duplication rate, showing how many extra copies arrived. These results gives us a quantitative like view of how well the system performed under the layer conditions. Moving on to the experiment right here. We tested two setups, the one experiment and another one. One with the where there's two layers, and where the MLE communicates directly with the PLE layer, and then a second one with 3 layers, basically where the MLE goes through a DLE layer that implements stop and wait before reaching the PLE. In the first setup, the measurement layer experiences the same effects as the physical layer, meaning we directly observe packet losses, duplications, and random delays. In the second setup, adding the data link layer hides most of the physical errors by resending lost packets and filtering duplicates. As a result, the loss and duplication rates drop pretty hefty, but the average delay might increase because of the retransmissions and acknowledgements acts take extra time. And if we wanted to run this experiment, we might do so. Oh, there we go. Might do so like this. We start the experiment. We'll send the 100 messages. Same thing over here. You just have to run this and just start the experiment. Now this takes quite a bit of time, so I'm not gonna stand here while while this runs. But as you can see, the packet losses and the packet duplications are visible because of the messages. Same thing here. You can see the ACK right here. Uh, and yeah, see the acknowledgements in this experiment, but not in this one because of the data link layer. So overall, the MLE class allows us to quantitatively evaluate network performance under the physical layer conditions. By comparing the two experiments, we can clearly see the trade-off between just latency and the actual reliability. The data link layer improves reliability, but at the cost of delay. These experiments effectively demonstrate how real world protocols balance some of these factors in network design. Thank you very much for the time.
So for section 5 of the project, we'll be demonstrating how to use iPerf3 to measure network performance. We are going to be doing 2 experiments. The first one is going to be testing communications between terminals on my own machine. The second one is going to test communications between my computer and a public iPerf3 server over the internet. So the first command we have to run is iPerf3s. This is going to start running a server on my machine. After this, we have to open a new terminal. So I'm going to be opening a new tab. On the second tab, we're going to be running the following command. It's going to be iPerf3c and then localhost as our IP address. So here we can see we start a TCP test, meaning it measures reliable data transfer between the client and the server. Since this is a local test, the connection is extremely fast and I should see speeds around 60 to 70 gigabytes per second. That's because the data never leaves my computer. After this step, we have a final step in this experiment. We have to open a third tab. This third tab is going to be for performing a UDP test on localhost. So we're going to be running the following commands. We have to test it with 100 megabytes, 1000 megabytes, and 10 gigabytes. So these were the results for our first test of 100 megabytes. Now we're gonna be running the exact same command but with 1,000. Finally, we're gonna be running this command once again but with 10 gigabytes per second. This was the last part of the first experiment. Now we're gonna be moving on to the second one. We're gonna go back to, it can be on any of our terminals, but let's go back to the first one. We're gonna be running iperf3c. And the public server that I chose was iperf3.moji.fr. In the port 5200. What we're doing with this command was performing a TCP test to a public server. Now we're gonna be doing a UDP test to the same server, this time using 10 megabytes per second and then 100 megabytes per second. So we're gonna be running iperf3c. Actually, I can just do this instead. Just add this parameters. So it says that the following server is running, it's basically running a test, so let's change this port to 5201. And finally, the same command, but with 100 megabytes. Seems like that port is also busy, so I'll just run it again, but with 5202. Okay, so to summarize what was done in this experiment, we found out how TCP tests show how fast data can be transferred reliably with every packet, and the UDP tests show the raw speed of the networks but may include loss or delay.